Okay, hello everyone. This video is going to be about the product form of the gamma function. And I'm going to assume in this video that you already know a bit about what the gamma function is, that you know a bit about integration by parts, and specifically I'm going to use the DI method for ease. And just knowing general things from Calculus 1, like using the natural log and exponential functions, will be useful, and that's all you'll need, as well as limits. So let's think about first what the gamma function actually is. Well, we're looking for it in our product form, but we can't find its product form until we know what its normal form is. So if I write gamma of z, that means the integral from 0 to infinity of e to the negative t times t to the z minus 1 dt. So t is a dummy variable here, a dummy variable of integration. And depending on our input, we're going to get different outputs. Now, just because this is an integral doesn't mean it's not still a constant. It is still outputting a number, and actually this number that it gives us, due to the fact that when we evaluate this, we integrate by parts, and we choose t to differentiate, and we bring the power down, and bring the power down again, and bring the power down again, and these powers accumulate as coefficients until eventually we get the output of the factorial of 1 less than our input, and that's what I've put here, z minus 1 factorial. So this is the definition of the gamma function as we normally see it, and it gives us a few interesting properties. So knowing that gamma of z is equal to z minus 1 factorial means that if we wanted to find another way of writing gamma of z plus 1, let's think about what gamma of z plus 1 means. Well, it's going to give us the factorial of 1 less than the input, which is going to be z factorial. But something interesting about the factorial function is that we can write z factorial as z times z minus 1 factorial. And we already know what z minus 1 factorial is, that's gamma of z. So we get this interesting property, which we might make use of either later or in another video. And that's also the property that's used to show that a half factorial, which is equal to gamma of 3 over 2, is equal to a half times gamma of a half, and gamma of a half can be shown to be the Gaussian integral, and that gives us that a half factorial is root 2 over 2. And so it's a really useful property to know about. But what we're looking for is a new way of expressing the gamma function, and specifically as an infinite product. Now, you may have come across infinite sums before. So let's say I have the sum from 1 to infinity of an, of kan, for example, or perhaps we'll do an to the k. Would just be summing up whatever an is to each power from 1 to infinity. And I'm sure many people have come across that before. You've probably seen product notation as well. Instead of using capital sigma, we use capital pi for product. And we would perhaps have the product from 1 to, let's say, 5. And if we were to say of k plus 5, what this would give us is 1 plus 5 times 2 plus 5, all the way up to 5 plus 5. And we can also have infinite products. So just like how we can use Taylor series and Maclaurin series to write a function as an infinite sum, we can also write functions sometimes as infinite products, and the gamma function is one of these. Now, the way we're going to approach this is first I'm going to define a new function which is very similar to the gamma function, and we'll see exactly how they're related in a minute. So my new function is gamma v of z. And gamma v of z I'm going to define as being equal to the integral of 0 to v, from 0 to v, of 1 minus t over v to the power of v times t to the z minus 1 dt. Now, apart from this little bit at the end, and both of them having a lower bound of 0, this may look different. It may be not immediately obvious what the relationship between the two is. But actually, you may recognize, or you may know, that e to the x can be written in its compound form as 1 plus x over n to the power of n as n approaches infinity, which implies that e to the negative t could be written as 1 minus t over n to the n as n goes to infinity. Now I've chosen to use v here instead of n, but notice how if I let v go to infinity, that's going to mean that my term here is going to become e to the negative t, and my v here is going to become infinity, which means that the limit as v goes to infinity of gamma v of z is equal to gamma of z. So right at the end, once we fully evaluated this issue, this problem, we're then going to take the limit as v goes to infinity so that we can say that gamma v of z is finally equal to gamma of z. But that's going to come at the end. And the reason that we do this and write e in its compound form will become apparent after we've had a look at integration by parts of this new integral gamma v of z. Now, when we integrate an integral like this by parts, we would always choose to differentiate t and integrate e to the negative t, and that's just because e to the negative t is easy to integrate, and t to the z minus 1 is something that can be diminished z minus 1 times until we get a very easy to evaluate integral, and from there things tidy up neatly. But in our case here, now that we've written e in a new way, we actually don't have to choose to do things in that order, because we've got another power here that we could eventually reduce to a constant, just in the way that we normally do with integration by parts. It's just the other way around. So I'm going to write out my di table, and this is a method that personally I think is going to speed things up, so that's why I'm using it, but you could use the normal integration by parts formula. It's exactly the same thing. This is just a simplified version of it. So I'm going to choose to differentiate 1 minus t over v to the power of v, and to integrate t to the z minus 1. So if we look at the right-hand column first, this is the easiest part to do because integrating this is extremely simple. We just add 1 to the power and divide by the new power. So integrating once will give us 1 over z times t to the z, and as you can see I've just added 1 and divided by the new power. If we do that again, I'm going to get 1 over z times z plus 1 times by t to the z plus 1. If I do it again, I'm going to get 1 over z times z plus 1 times z plus 2 times t to the z plus 2. And now that hopefully you have a good understanding of how this is working, I'm just going to do a dot 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 because we get the idea and we know what the pattern is now. So let's look at the term that we're differentiating this. So I'm just going to choose y to be equal to 1 minus t over v to the power of v. And we know that using chain rule, dy dt is equal to the derivative of the inside with respect to t times the derivative of y with respect to whatever we've chosen to be in the inside. A nice way to say this is, let's say I'm going to choose u to be equal to 1 minus t over v, and that implies that y is just now equal to u to the v, and dy dt is equal to du dt times by dy du. And you can see the cancellations going on here very nicely. So we just need to find du dt and dy du. Du dt just comes from differentiating this part with respect to t, which we can do quite easily. 1 is a constant, and here we've just got a t, so we'll be just left with the coefficient upon differentiating, which is negative 1 over v. And the derivative of y with respect to u is equal to, well, this is just power rules. So we're going to bring the power down and subtract 1 from the power. So we're going to get v times u to the v minus 1. So we now know that dy dt is equal to negative 1 over v times u to the v minus 1. And so we've got a 1 over v here and a v there, which are going to cancel, and those two are going to become 1. So for our first derivative, we've ended up with negative u to the v minus 1, bearing in mind that u is just this bracket that we started with without its power. It's this internal part of the function. That implies that our first derivative is negative 1 minus t over v to the power of v minus 1. Now we could go through that whole process again to find what the second derivative is, but we can kind of start to get a feel for how things are going to work, because this bracket that we're substituting for u is staying the same each time. So the derivative of u with respect to t is always going to be negative 1 over v, which means that as we keep going, this is going to compile. So for the second derivative, we'll have another negative 1 over v. For the third derivative, we'll have another, which will give us 1 over v squared. For the fourth derivative, we'll have another, which will give us negative 1 over v cubed. So we can see that we're going to have a power of v on the denominator, which will be increasing after the first derivative, and that we're also going to have alternating negative signs. The only other thing we need to consider is what's the derivative of y with respect to u. So that's just treating this bracket as if it were what we're differentiating, just ignoring everything that's in it, just as if it's one term, and just using power rule. And that's going to lead us to keep bringing down the power and minusing 1 from the power each time. So using that, we can find that the second derivative will be, well, negative 1 over v times negative 1 is just going to be 1 over v. And we're also going to bring the power down, and we're going to get v minus 1, and then we have to take 1 away from the power. So we get a v minus 2 up here. If we do it again, we're going to get a negative now, v squared times v minus 1, v minus 2, 1 minus t over v to the v minus 2. And now that we have a good grasp of what's going on, I'm going to say that we can just put a dot 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 here. So notice that with the DI method, we always add and then subtract and then add and then subtract across the diagonals. And all of our subtractions across the diagonals are coinciding with our negatives in the D column, which means that actually we're just going to be adding all of these things multiplied together. And if we write out, I'm going to write out the first two. So we have that gamma v of z is equal to 1 minus t over v to the power of v times t to the z over z, plus our next term, which is 1 minus t over v to the v minus 1, t to the z plus 1, divided by z times z plus 1. I'll do one more just so we can start to get a better idea of the pattern. Plus v minus 1 times 1 minus t over v to the v minus 2, t to the z plus 2 over v times z plus 1 times z plus 2. And just to be clear, I've just gotten this by multiplying along the diagonals of the column, which is just shortening having to do the long work for integration by parts. Now, if we were to keep going here, where would we stop? Well, we'd stop when we've differentiated this term enough times that it no longer has a power which is v, that instead it just has a power that's 0. Because notice that each time we differentiate, we're subtracting 1 from the power. And just notice that that should actually be a negative 3 there. And that means if we keep going, that by the time we've done it v times on the vth derivative, we will have finally gotten a power which is v minus v, or in other words 0, and therefore this term will be 1. We'll be left with a nice thing to integrate, and we've got our sum, the sum that we're looking at. So let's think about what the vth term in this sum would be. So let's just look at the patterns. The first time that we integrated, we can see we had a z. The second time we had a z plus 1. So on the vth time that we do it, we're going to end up with a t to the z plus v divided by z times z plus 1 times z plus 2, all the way up to whatever z plus v is. So the I part is quite simple. The D part, we've got to remember that we're going to have a 1 minus t over v to the v minus v, but that's just 1, so I'm not going to write that. What we are going to be left with though is, don't forget that our v's in the denominator have been increasing in power each time. You can see that on the first derivative here, we don't have a v. On the second derivative, we have a v to the 1. On the third derivative, we have a v to the 2. So that means that the derivative that we're on is 1 more than the power of our v on the denominator. In other words, we're going to have v to the v minus 1, because we've got 1 less. If we've done it v times, the power on the denominator will be v minus 1. And we've just got to think about what we've got by bringing the power down from differentiating our term here each time. Well, we've had v minus 1, we've then got v minus 2, we're then going to have v minus 3, v minus 4, v minus 5, v minus 6, all the way up to times 3 times 2 times 1. And you'll be familiar with the fact that that is just v minus 1 factorial. So there we go, that's our final term in our sum. And we no longer need our DI table, so I'm going to make some space by rubbing that out. And it's very easy to get stuck at this point wondering what to do, because we're looking for a product form, we're not looking for a sum. And we're also looking to take the limit as v goes to infinity, and that would be very messy to do with this huge sum. But what we've got to remember is that this is a bounded integral, it's definite, which means that we're looking at this sum between the bounds of v and 0. So let's look at how this behaves. We know from the fundamental theorem of calculus that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So we've got to plug in v to this whole expression and then subtract whatever we get when we plug in 0. So I'm actually going to look at the lower bound first. We're going to look at what happens when we put t as 0, because it's actually something that's very easy. You can see our first term has a t to the z, our second term has a t to the z plus 1, our third term has a t to the z plus 2, and our vth term has a t to the z plus v. So every single term in this sum, no matter what v is going to have a t on the numerator, which means that when t is 0, each one of those things that we're adding, these fractions, will be 0, and therefore the entire thing will just be 0. So we know that capital F of 0 is just 0, so all we need to find out is what capital F of v is. Now that's what happens when we put all our t's for v's. So, okay, putting t as a v here for our t to the z's and our t to the z plus 1s up to the t to the z plus v's isn't going to make a huge difference. That's not going to be the issue. What will be an issue though is our bracket here. Because when we put t as v, what we're calculating is 1 minus v over v to the v minus 1. In other words, 1 minus 1, or in other words, 0. So that would imply that every single term in this summation is 0, and at the upper bound and lower bound, which would mean the whole thing will go to 0. But we've got to remember one crucial thing. There's only one term in this sum where we don't have the issue of having to deal with this 1 minus t over v bracket sum power. And it's the vth term. Because by the vth term, we've reduced the power of this bracket so much that it's 0 and it's now 1, and we don't have to worry about it anymore. And that means that evaluated at f of v, this entire integral is just equal to the vth term of the sum where t is equal to v. In other words, v minus 1 factorial times v to the z plus v over v to the v minus 1 times z plus 1 all the way up to z plus v. So let's make some space now to have a look at what this is telling us. So what we've just said is that gamma v of z is equal to v minus 1 factorial times v to the z plus v over v to the v minus 1 times z plus 1 all the way up to z plus v. And there's a little bit of nice simplification that we can do here. If we multiply by v on the top and the bottom, remember that v minus 1 factorial times v is just v factorial, which means that we get on the top a v factorial times v to the z plus v. And when we multiply by v on the bottom, we just add 1 to the power of the v we've already got. And v minus 1 plus 1 is just v. So we end up with a v to the v on the bottom here. And you may already see where this is going. But we've got a v to the v on the top and a v to the v on the bottom. So after a bit of cancellation, this is the form that we've been left with. V factorial times v to the z over z times z plus 1 times z plus 2 all the way up to z plus v. And this is kind of a nice formula. We're getting there because we're dealing with a product here on the bottom. Factorials are just also repeated multiplications. So it seems that we're getting close. But I'm going to do something now, which may seem counterintuitive, or just like a step that's come out of the blue, but we'll see why it's important later. I'm actually going to take the reciprocal. And we've got to remember later down the line that we've taken the reciprocal. But I'm going to say that implies that 1 over gamma v of z is just equal to this fraction flipped over. So the denominator will now be v factorial times v to the z. But I'm going to rewrite out this bit using our capital Pi product notation that we spoke about at the start of the video. So I'm going to leave my z out, and I'm going to say it's the product from 1 to v of z plus k. And you can see that will just generate for me this sequence here, z plus 1, z plus 2, all the way up to z plus v. But as I said, factorials are just repeated multiplication. So we've got to see what's going on here with the product and the factorial. And let's have a look at this fraction. I'm going to do this in a different color just to show that we're kind of taking a sidestep here. So on the top, we've got our product from 1 to v of z plus k, and on the bottom we've got v factorial. Let's think about what this can be rewritten as. So this product on the top we know is just z plus 1 times z plus 2 all the way up to z plus v minus 1 times z plus v. And v factorial is equal to 1 times 2 all the way up to v minus 1 times v. And you might see what I'm getting at here, but at each kind of factor on the top, on the numerator, there is a corresponding factor on the denominator, which causes us to have quite a nice cancellation, seeing as both of them are repeated multiplications up to v. So for the first one, that leaves things unchanged. We get left with a z plus 1. But for the next one, we get left with a z over 2 plus 1. For the next one after that, we'd have a z over 3 plus 1. And for the vth term, we'd have a z over v plus 1. So we can see now, returning to our original expression, that if we write our z and 1 over v to the z as just z times v to the negative z, then we get left with just our fraction of the product over v factorial, this bit, which we've just said is equal to a different kind of product. Now, how could we write that product? Well, it seems to me that we're doing z over k plus 1 all the way up to v. And so now we've just done a little bit more simplification. And we have 1 over gamma v of z being equal to z. And here's, I'm going to use a little bit of that natural log exponential thing I was talking about. This is the only place you'll probably need it, apart from one time later on, which is linked to this. I'm going to write v to the negative z as e to the negative z ln v. And you'll see why this is an important step next. Multiplied by our product from 1 to v of 1 plus z over k. Okay, we're making progress. Remembering that our intention is to let v approach infinity so that gamma v of z is equal to gamma of z, we've just got one issue, and that is this v. This v here, if I let v go to infinity now, this is going to pose an issue because this is going to get us 0, because e to the negative of anything approaching infinity will approach 0. So I've got to think of a way to deal with my negative ln v here, some kind of limit that I can take that involves a natural log that's actually going to give me a constant that's not going to make something blow up or whatever the opposite of blowing up is. And actually that lies in a constant which some of you may have seen before called the Euler-Mascheroni constant. And it's denoted by little gamma, and it is the limiting difference, as I'll use v, as v approaches infinity, of the harmonic series, which is just the sum of the reciprocals of all the integers, which does diverge, it blows up, minus the natural log of v, which also blows up. But these two grow towards infinity such that there is a limiting difference and it's a constant, which is called the Euler-Mascheroni constant. I think it's something like 0.557, I'm not exactly sure. But we're going to make use of this limiting difference. So we've got a z here. Well, that's okay, we could always factor a z out and have z times the Euler-Mascheroni constant is equal to z times this limit. So what am I missing? What am I missing in my exponent to generate this constant? Well, I've got the negative ln v. I just need this harmonic series multiplied by z, of course, so that it will factor correctly. So really, I need to introduce this z times the sum from k equals 1 to v of 1 over k. So that when I take my limit as v goes to 0, I don't get something blowing up, I get a nice constant. So actually, I'm just going to choose to multiply by e to the z times that series. And that's going to give me z times e to the z times that series from 1 to v of 1 over k minus ln v. Now at this point, if you're not suspicious of what I've just done, then you must be lost. We can't just multiply by some sum as an exponent of e and assume that's not going to change the value of our expression. It is. And if we've multiplied by e to the z times this sum, which I'm going to call s, then we need to also multiply by e to the negative zs, so that overall no change has been done. Okay, we might have added something to the exponent here, but we've undone it elsewhere. So how are we going to introduce this e to the negative z times this sum? Well, it's by noticing that addition with exponents is just multiplication of their bases. In other words, if I expand this sum, what I'm looking at is e to the negative z minus z over 2 minus z over 3 minus z over 4, etc. And this can be written as e to the negative z times e to the negative z over 2 times e to the negative z over 3 all the way up to negative z over k. And there we go, we've got another form of repeated multiplication up to v, because we want it to happen up to v, so that it counteracts this sum up to v. And so, since we've already got some infinite multiplication, or not infinite yet, but multiplication going up to v here, we can just slide in an e to the negative z over k, and this will now perfectly counteract the series that we've added here. So that means that this expression is actually unchanged from the one above. We've just introduced something that's going to aid us in taking the limit. And I think we're actually at that point now. So remembering that we're looking at the reciprocal now, that implies that 1 over gamma of z is equal to the limit as v approaches infinity of 1 over gamma v of z, which is equal to the limit as v approaches infinity of our expression here. And let's think about what that would be. Well, z is unaffected. E to the z times this limiting difference, well, we know that's the Euler-Mascheroni constant, times by the product from 1 to what's now infinity of 1 plus z over k times e to the negative z over k. So we've now reached our final form of the gamma function. This is its infinite product form, also known as the Weierstrass product. And it's useful in lots of different proofs. One of the best ways to use it, I think, is to prove Euler's reflection formula, which states that gamma of z times gamma of 1 minus z equals pi over sine pi of z. And that's what I'm going to make the next video on this topic about. Another way this is useful is in a function called the digamma function. To lead you towards looking to that yourself, note that gamma of z is actually equal to that whole expression that we just spoke about, all to the power of minus 1, since we're dealing with reciprocals. Think about taking the natural log, bringing that power down, and then remembering that multiplication inside of the natural log is addition outside. And also then remembering that if I have the natural log of a function then the derivative of that is going to be the derivative of the outside, which is going to give me 1 over f of x, times the derivative of the inside, which is f prime of x. Which means that if I then differentiate the natural log of the gamma function, I'm going to get gamma prime of z divided by gamma of z. And this is the digamma function. And there's also the trigamma function and also the polygamma function, which are all related in the same way. Perhaps we'll cover that in the video after Euler's reflection formula. But I hope this has been useful. Thanks for watching and see you soon.